Hi, welcome to problem set 5 on momentum. This is a single chapter unit, and there'll be several types of problems in the chapter, so good luck. On April 15th, 1912, the luxury cruise liner Titanic sank after running into an iceberg. What momentum would the 4.23 times 10 to the 8 kilogram ship have imparted to the iceberg if it had hit the iceberg head-on with a speed of 11.6 meters per second? Actually, the impact was a glancing blow only. Well, the momentum times the momentum equals the mass times the velocity, 5 times 10 to the 9th kilogram meters per second. If the captain of the ship had seen the iceberg a kilometer ahead and had tried to slow down, would this have been a futile effort? Yes, it was just too much momentum. The size of the ship, the mass of the ship, plus the high rate of speed, it would have been fruitless. Auto companies frequently test the safety of automobiles by putting them through crash tests to observe the integrity of the passenger compartment. If a 1,000 kilogram car is sent towards a cement wall with a speed of 14 meters per second and the impact brings it to a stop in 8 times 10 to the negative 2 seconds, that's 8/100ths of a second, with what average force is it brought to a rest? Notice it's stopping. So it's going to be final minus initial velocity, 0 minus 14, multiplied through negative 14,000 kilogram meters per second. So that's going to be the change in momentum. Now, if I did it in 8 times 10 to the negative 2 seconds, you divide through, and you would get negative 175,000 newtons. So that would be the force delivered as a result of that stopping so quickly. The longer the period of time, the longer the period of time, the lower the force would be. And you might want to put in some numbers to see if that's true. Rhonda, who has a mass of 60 kilograms, is riding at 25 meters per second in her sports car when she must suddenly slam on the brakes to avoid hitting a dog crossing the road. She is wearing her seatbelt, which brings her body to a stop in 0.4 seconds. What average force did the seatbelt exert on her? Now, you'll see that the momentum on her is negative. So the seatbelt will be positive. And this is 0 minus 25 is where you get the negative. So that's negative 1,500 kilograms meters per second. And then you know that the momentum change equals the impulse, which equals negative 1,500 kilogram meters per second. And just the impulse equals negative 1,500. So if I divide through by 0.4, I'll get negative 3,750 newtons, and that's the force her body is exerting on the seatbelt, and the seatbelt will be exerting a positive 3,750 newtons. So that's the answer to A. If she had not been wearing her seatbelt and the windshield had stopped her head in 1 times 10 to the negative 3 seconds, what average force would the windshield have exerted on her? So the average force the windshield would have exerted on her would be that original value, 1,500 kilogram meters per second, 1,500, and then you would divide through by 1 times 10 to the negative 3 seconds, and that would be considerably higher, and that'll be plus 1,500,000 newtons. Now, I am 1,000 newtons, so that's pretty deadly. How many times greater is the stopping force of the windshield than the seatbelt? And it will be 400 times. Just do the math. So that should be actually positive over positive, but those are the forces exerted by the body. So either way, it's going to be a positive 400 times. Next, on October 17, 2006, the population of the United States reached 300 million. If all of those people jumped up in the air simultaneously, pushing Earth with an average force of 800 newtons, each for a time of 0.1 seconds, what would happen to the 5.98 times 10 to the 24th kilogram Earth? Interesting. So there is going to be the change in momentum. It'll be 3 times 10 to the 8th times 800 times 0.1. That'll be the impulse, which is the same thing as the change in momentum. And that's going to be 2.4 times 10 to the 10th Newton seconds. And then divide through by the mass of the Earth, and you'll get, anyway, you're saying that the impulse is going to equal m delta v, and delta v equals 4 times 10 to the negative 15th meters per second. So you see that it's pretty negligible. That's what would happen, very negligibly. It would change it. In Sharkey's Billiard Academy, Maurice is waiting to make his last shot. He notices that the cue ball is lined up for a perfect head-on collision as shown. Each of the balls has a mass of 0.08 kilograms, and the cue ball comes to a complete stop upon making contact with the 8 ball. Suppose Maurice hits the cue ball by exerting a force of 180 newtons for 5 times 10 to the negative 3 seconds, and it knocks head-on into the 8 ball. Calculate the resulting velocity. Okay. Well, the change in velocity is going to be 11.3 meters per second. Well, the way you get that is that you're saying that it says, suppose Maurice hits the cue ball by exerting a force of 180 newtons. So that's going to be the force. The time that the duration of the collision is going to be 5 times 10 to the negative 3 seconds. So that's the impulse, which is equal to the momentum. So you're going to divide by the mass, and that's going to give you the change in velocity, which is 11.3 meters per second, because as you know, the two things are equal. The change in momentum is equal to the impulse. And since the balls each have the same mass, the second ball acquires a velocity of 11.3 meters per second, and the first comes to a rest. But just remember, the change in momentum equals the impulse. So this problem is predicated upon that idea. Okay, now, during an autumn snowstorm, a 0.012 kilogram hailstone traveling at 20 meters per second made a 0.20 centimeter deep dent in the hood of Darnell's new car. What average force did the car exert to stop the damaging hailstone? Well, you know what the distance is, and the distance is going to be 0.20 centimeters, or 0.0020 meters. You know what the average velocity is, because this equation is, remember, for average velocity. Remember that back in September, and that's 10 meters per second. Not 20, it's 10, that's the average. And then that value is going to be 2 times 10 to the negative 4th seconds. So you see that it's the duration of the collision is very, very, very small. The smaller the duration, the greater the force. So expect a large force because of that small duration. Remember, force and time are indirect to one another. All right, so now we know what the change in momentum is. It's going to be 0.012 times 20 meters per second. That's going to be the change in momentum, and that's going to equal the impulse. We know delta t. We don't know F, so we can divide through, and we will get a number that is easily in excess of 1,000 newtons. So it's going to be about 11 or 1,200 newtons. So because it's divided by a very small number. So that's it, 1,200 newtons, and that's very large. And again, the shorter the duration of the impact, the larger the force is going to be. So just remember, this problem, you can do this because you have four possibilities. You have mass, change in velocity, force, and change in time. So you need at least 3 of those 4 in order to do it, and you have the mass and velocity, and then you simply use that and divide by the time, and that gives you the force. Okay, Jamal is at a state fair playing some of the games. At one booth, he throws a 0.5 kilogram ball forward with a velocity of 21 meters per second in order to hit a 0.2 kilogram ball sitting on a shelf, and when he makes contact, the bottle goes flying forward at 30 meters per second. What is the velocity of the ball after it hits the bottle? So what is the velocity of the ball after it hits the bottle? What's the final velocity? So remember the conservation momentum. The total initial momentum is going to equal the total final momentum. Look at that. It says mass and velocity initial for bottle, that momentum, plus the mass velocity initial for the ball. That sum is going to equal the final sums. So what we want to solve for is the final the final velocity of the ball all the way on the right. So I'm simply putting the finals on the left and the initials on the right. You don't have to do that, but I'm just simply going to isolate the variable V bottle F, the second term from the left. I'm going to now subtract the final momentum of the ball from the right. You see how I did that? And now I'm going to divide through by mass, and that will allow me to solve for V ball F, final velocity of the ball. So that you'll see I'll set up a quotient, and that'll be equal to the final velocity of the ball. So now, and I'm going to do this for every problem. I'm going to go through the same kind of derivation. Make sure you can do this. Oftentimes a quiz is going to be, in class, simply not even plugging in values, just solving for the equation, and I'll let you know what that is. For instance, in this particular case, I'll say, write the equation in terms of, write the equation for solving for V final for the ball, for instance. And your answer on the quiz will be that on the bottom. That will be your answer. And you'll have to have everything in that in a proper place. So now all I'm going to do now is I'm going to let this run, and you can observe how I'm going to do this. Now it's just simply going to be plugging and chugging. I'm going to put in the mass of the bottle, the velocity of the bottle initial, the mass of the ball, the velocity of the ball initial, etc. So just keep in mind B as we're doing this. If the bottle were more massive, how would this affect the final velocity of the ball? And we're going to answer that question, but I just want you to keep in mind as we're calculating this. So now I'm just going to let it run. I'm going to be quiet, and I'll let you see if you can come up with V-ball final before it comes up on the slide. You can see everything's plugged in. Look and see, you see the initial velocity of the bottle, because it's sitting still on a shelf, is going to be 0. That kind of simplifies things considerably. So, good luck. So you can see the final value is 9. That's 4.5 divided by 0.5, and that'll be 9. So 10.5 minus 6 divided by 0.5 is 9 meters per second. So that'll be the final velocity of the ball. So it's slowing considerably, and some of that momentum was transferred to the bottle. Okay? So it went somewhere. It went somewhere. And that's the answer. Now, B says, if the bottle were more massive, how would this affect the final velocity of the ball? Well, let's go back and look at the equation. It's probably simplest to do that. How would the bottle were more massive? How would this affect the final velocity of the ball? Well, it's essentially, look at the far right hand side where it says minus 0.2 kilograms times 30. So instead of being 0.2, it was 0.4. So you would be subtracting off a larger amount. See, so it would be, the first term in the numerator is 0, but then the third term would be larger, and you'd be subtracting off a larger number. So the ball's final velocity would be less. The ball's final velocity would be less. Jeanne rolls a 7-kilogram bowling ball down an alley for a league championship. One pin is still standing, and Jeanne hits it head-on with a velocity of 9 meters per second. The 2-kilogram pin acquires a forward velocity of 14 meters per second. What is the new velocity of the bowling ball? Now, remember that momentum is conserved. So the initial momentum of the ball plus the initial momentum of the pin is going to equal the sum of the final velocities and final masses of the ball and pin. So, what do we want to solve for? This is just like the last problem. What is the new velocity of the bowling ball? So I want to solve for the velocity of the bowling ball final. So what I may do is just simply flip the equation according to the property of symmetry, the mathematical property of symmetry, and say that the sum of the final momentums is going to equal the sum of the initial momentums. Now remember, regardless of what they are, the sums of the initial equals the sums of the final. And you'll see that this is very similar to the last problem we did, and it's going to be the same exact setup, where the sum of the initial velocities minus the momentum of the pin divided by the mass of the ball is going to equal the velocity of the ball final. So now we're going to plug in. Don't forget that the initial velocity of the pin is 0. So it's going to be 7 times 9 plus 0 minus 28 divided by 7. And that will, when you calculate that out, that'll be the final velocity of the ball. So I'll let you see if you can calculate that out before an answer actually shows up. Oh, there it is. So it's 5 meters per second. So just remember, what we're doing right now is conservation of momentum, and that's the hardest concept in the chapter. You have 3 major concepts. The first is the definition of momentum, mass times velocity. The next one is the change in momentum. All right, let's do this first. Running at 2 meters per second, Bruce, the 45-kilogram quarterback, collides with Biff, the 90-kilogram tackle, who is traveling at 7 meters per second in the other direction. Upon collision, Biff continues to travel forward at 1 meter per second. How fast is Bruce knocked backwards? So we want to, again, write this in terms of the conservation of momentum, and the initial momentum of Biff plus the initial momentum of Bruce is going to equal the final momentum of Bruce plus the final momentum of Biff. So again, the next concept is going to be change in momentum and impulse. And then the third concept is this. It's the conservation of momentum. So what we want to do is, this is the third problem that's very, very similar. And this is right out of problem set 5. So it's just like this. And again, you're going to plug in chug, essentially. So running at 2 meters per second, Bruce, the 45-kilogram quarterback, collides with Biff, the 90-kilogram tackle. So now it's going to be 90 times 7 plus 45 times negative 2 minus 90 times 1. Now everything is in motion here, so there's nothing is going to cancel out. So the quarterback is in motion, Biff is in motion. So this is slightly different than the previous 2. And then Bruce is going to be going 10 meters per second the other way. That seems awfully... that seems pretty large, actually. I'll have to check that answer. But anyway, that's what we have, 10 meters per second for the velocity of Bruce going backwards. Somehow I don't think that's correct, but we will check that out. Okay. And waiting for exercise 10. Anthony and Sissy are participating in the Roll-a-Rama roller skating dance championship, while 75-kilogram Anthony roller skates backwards at 3 meters per second. 60-kilogram Sissy jumps into his arms with a velocity of 5 meters per second in the same direction. How fast does the pair roll backwards together? So similar, again, similar, but this time it's a little bit different. The final velocity of Anthony and Sissy are the same. So you're going to be able to factor out the velocity of Anthony and Sissy from the right. So you can factor that out. So it'll be the final velocity on the right will be the velocity of the pair times the quantity, mass of Anthony plus mass of Sissy. So that's not going to be a problem. And then you want to simply divide both sides by the sum of the masses. So you're going to get the velocity of the pair equals the sum of the initial momentum divided by the sum of the masses. And here I'm using the property of symmetry, and just flip-flopping things. And then I'll divide the sum of the initial momenta, plural momenta, singular momentum, divided by the sum of the masses of Anthony and Sissy. And then you're going to plug in. So I'll let things go on from here, see what you can do. I will be silent in the background, and good luck. And the answer is 3.9 meters per second. B says, if Anthony is skating towards Sissy when she jumps, would their combined final velocity be larger or smaller than your answer to part A, and why? Well, we said that in the last problem that Anthony was moving backwards, but that was actually positive because his body is orientated backwards. But he's moving positive direction. If he's moving towards Sissy, he's moving in the negative direction. So if you see in the numerator where 75 times 3 is positive value, that would be a negative value because 3 would be negative. Also, if you think about it conceptually, they would be moving towards each other and they would cancel each other out a bit. So as a result, if he's changing direction, in both mathematically and conceptually, you can see that the answer would be smaller. The velocity would be smaller. So look at it again. Look at the value again, because momentum is a vector, and it's important to be able to think in vector terms. So even though Anthony's going backwards, his body is orientated backwards, but it's the initial direction, so the 3 meters per second is going to be positive. If he's going in the opposite direction, he would be negative. So the left term in the numerator would be negative, so the entire numerator would be less, and the velocity of the pair would be less, so smaller, because of the total momentum would be less. Now, to test the strength of a retainment wall designed to protect a nuclear reactor, a rocket-propelled F-4 Phantom jet aircraft was crashed head-on into a concrete barrier at high speed in Sandia, New Mexico on April 19, 1988. The F-4 Phantom had a mass of 19,100 kilograms, while the retainment wall's mass was 469,000 kilograms. The wall sat on a cushion of air that allowed it to move during impact. If the wall and the F-4 moved together at 8.41 meters per second during collision, what was the speed of the F-4 Phantom upon impact? So we're going to kind of do this a little bit faster in terms of getting the equation together. But essentially, the initial momentum of the system is going to be contributed by the aircraft. That massive wall initially has no velocity, so that term will drop out. So the final momentum will be the mass of the aircraft and wall together times the 8.41, whatever it had said. Here is the jet crashing into the retainment wall, and it's able to move. The retainment wall is able to move. Otherwise, it would be an enormous force on the retainment wall. And the bottom picture, of course, is the final explosion. We see the initial impact. The initial momentum is the sum of the wall and the aircraft, and the wall's going to cancel, obviously. And the final momenta is a combination. It's actually one momentum, and it's going to be the velocity of the pair times the sum of the masses. And you're going to subtract off the momentum of the wall from the right side, which is 0 anyway. And then you're going to divide through by the mass of the jet. That's how you got that. So the numerator of that bottom equation is going to be actually the right side of the top equation after you manipulate it. And then you're going to divide through by the mass of the F4 Phantom jet. Now, what you're really looking for is the initial velocity, the F4. And it's always good to do this anyway, because the equation tells you so much about what's going on. Here we're plugging things in, and you can see the right term, far right term, in the top, in the numerator, cancels, and you're left with, grind it out, and you're left with 215 meters per second, which is rather significant. It's not the speed of sound. The speed of sound is 330, but it's actually very large. Exercise 12 reads, Valentina, the Russian cosmonaut, goes outside her ship for a spacewalk, but when she is floating 15 meters from the ship, her tether catches on a sharp piece of metal and is severed. Valentina, who tosses her 2-kilogram camera away from the spaceship with a velocity of 12 meters per second. How fast will Valentina, whose mass is now 68 kilograms, travel toward the spaceship? So this is Newton's third law. Valentina wants to go towards the ship, so she's going to throw the camera away from the ship. She pushes on the camera pushes on her. The camera will go one way, she'll go the other way, back to the ship. So this is the conservation momentum of the camera and Valentina, initial and final. The sum of the initial momenta will equal the sum of the final momenta. And the initial momenta will be 0, and I want you to consider why the initial momentum will be 0. The sum of the initial momentum will be 0. Why? And then what happens mathematically. So what I'm going to do is I'm going to let this run, see if you can sort it out, see if you can make some decisions, and we'll see what happens. You see, even if the initial momentum is 0, the momentum of the camera, the final momentum of the camera, and the final momentum of Val has to equal 0. They have to be equal and opposite. So they have to be the same. The magnitudes have to be the same. They have to equal 0. So now we can set one against the other, and let's watch that happen. And it'll make sense. It'll make sense. Let's watch. Now, what are we going to do with the mass of Valentina? Remember, we're calculating the final velocity of Valentina. And then why are we given the distance? Have you wondered about that? Why are we given the distance? So you can see that the velocity of Valentina is going to be negative. It could be either one. You just have to pick one. But Valentina is the one that's creating the scene. She's throwing the camera in a particular direction, so that's going to be positive, and she's going to be negative. It could be vice versa. You have to declare that in the beginning and then be consistent with that. So then let's plug in and see if we can get this done. Why don't you plug in and see if you can get the right answer. So that's the velocity. So if she's going at that velocity and she has to go 15 meters, how long is it going to take her to make her way back? So here reminds you that they're going in opposite directions. The camera is moving at 12 meters per second and she's going to be moving at 0.35 meters per second. Remember, the camera is one mass, is a small mass, and she's a larger mass. So remember, they have to be equal and opposite. So how long is it going to take her to get back to the spaceship? Assuming the spaceship remains at rest, with respect to Valentina, how long will it take her to reach the ship? So what is the equation for velocity, and how is it rearranged for time? "43 seconds, and I'm sure it seems like a lifetime for Valentina." A 620-kilogram moose stands in the middle of the railroad tracks, frozen by the lights of the oncoming 10,000-kilogram locomotive that is traveling 10 meters per second. Then the engineer sees the moose but is unable to stop the train in time, and the moose rides down the track sitting on the cow catcher. What is the new combined velocity of the locomotive and the moose? Remember, there's no danger to the moose. The moose is just going along for the ride, I'm sure. So, what is the new combined velocity? Now, here I wrote this in terms of ones and twos, and I'm going to leave it to you to come up with a designation of what's one and what's two. So, the case is still the sub-zero, 1 sub-zero, that's still naught, that's initial. So the sum of the initial momenta equals the sum of the final momenta. And you've got to decide which is which and then just be consistent. Okay. So what we're going to do is, on the right side of the equation, we can factor out the final velocity because it's going to be of the moose and the train. That's on the right side. The final velocities are going to be the same for the moose and the train because they're together, because the moose is riding on the train cowcatcher. So then we want to solve for, we're going to divide both sides by the sum of the train and the moose. So here I've rewritten it in terms of the moose is going to be 1, the locomotive is going to be 2, and then you have the combined factored out from the sum of the masses of the moose and the locomotive. So it's going to be the sum of the initial momenta divided by the sum of the masses of the moose and the locomotive is going to be equal to the velocity of the combined train and moose. And there's the values plugged in. 0 is the initial momentum of the moose because he's standing still. He's frozen on the track. So let's do a calculation and see if you can do it before I do. So what is going to be 100,000 divided by 10,620? What's going to be the answer to that? Did you get it yet? You see that it's going to be somewhere less than 10. But who's counting? And it's going to be 9.42. Hope you could do that mathematically in your head. Okay, let's do exercise 14. But let's just review the facts. So you can see that the speed of the train is not reduced that much because the train is so enormous compared to the moose, even though that's pretty heavy for a moose. I mean, I weigh 100 kilograms, that's pretty heavy. So it should make sense to you when you're finished. Leah's rolling on her 4-kilogram skateboard with a constant speed of 3 meters per second when she jumps off the back and continues forward with a velocity of 2 meters per second relative to the ground. This causes the skateboard to go flying forward with a speed of 15.5 meters per second relative to the ground. What is Lee's mass? Well, again, we haven't gone back to this, but the initial momenta, the sum of the initial momenta is going to equal the sum of the final momenta. So that's what this is based on. That's what all the problems on the conservation of momentum are based on. They're based on this very simple equation, rho naught equals rho final, or the sum of the initial equals the sum of the final. So start writing out an equation. There we go. We have some more 1s and 2s. You've got to decide which is which. And this is going to be a little different because this causes the skateboard to go flying forward with a speed of 15.5 meters per second relative to the ground. What is Lee's mass? So this is kind of a little bit of a unique problem because you're not calculating a velocity, you're calculating an individual mass. So is one going to be Lee or is one going to be the skateboard? Okay, I've chosen 1 to be the skateboard and 2 to be Lee and Lee's mass and velocity. So I want you to do this problem yourself. See if you can get it done. I certainly have this before we even go to the next slide. Put this on pause and see what happens, and you won't hear my voice until the final answer. So you can see what's happening here already. Gathering and trying to isolate Lee's mass. So you're going to have a quiz actually very soon. If where you're going to have to isolate these kind of variables. So you have to get Lee on the left and the skateboard on the right, and then you can factor out the mass of Lee and then divide through. Factoring out the mass of the skateboard just makes it a little bit easier to calculate, but not much more. But you've got to factor out, you've got to rearrange the equation so you can factor out the mass of Lee, and that's exactly how you do it. Okay, so there are the values plugged in, and you're going to calculate the mass of Lee. And it should make sense. I mean, Lee's probably a kid, he's probably somewhere around 60, 70 kilograms, or maybe Lee isn't a kid, but I'm 100 kilograms, so look at the values for the velocities and see if you can come to some understanding. So it's going to be mass 2. That's what's plugged in, and I'm going to rearrange that. And 15.5 minus 3 is 12.5 times 4, which will be 50, divided by 1. So it'll be 50. She's 50 kilograms. Hopefully you can do that in your head. Okay, that's the final answer, 50 kilograms. You'll see that M2 is going to be Lee's mass, and 50 over 1 is going to be 50. And we'll take a break, and you know what? You'll never know I was gone. And there it is. M2, or Lee's mass, is 50 kilograms. Be right back. A1, Bernie, whose mass is 70 kilograms, leaves a ski jump with a velocity of 21 meters per second. What is Bernie's momentum as he leaves the ski jump? Well, it's not asking for a change in momentum, it's just asking for momentum. And momentum is mass times velocity. That's all it is, nothing more, nothing less. So, as a result of that, it's going to be 70 times 21. So, the momentum equals mass times velocity, and then it's going to be 70 times 21, which is going to be about 70 times 20, which is 140, 1,400, and then 1,470, and another 70, and that's the answer. So, what is the Bernie's momentum as he leaves the jump? It'll be 1470 kilogram meters per second. Ethel is sitting on a park bench feeding the pigeons when a child's ball rolls towards her across the grass. Ethel returns the ball to the child by hitting it with her 2-kilogram pocketbook with a speed of 20 meters per second. If the impact lasts 0.4 seconds, with what force does Ethel hit the ball? Well, we see that it's going to be a momentum of 40 kilogram meters per second. And that's going to equal F delta T, which is going to be F 0.4. So, if you're going to divide the 40 by 0.4, you're going to get 40 divided by 0.4, which is going to be, what? How many newtons? What's the force that's going to be? So see if you can calculate that. That'll be 100 newtons. Because 4 would be, 40 divided by 4 would be 10, but it's 0.4, so it'll be 100 newtons, which is a significant kick. When Reggie stepped up to the plate and hit a .150 kilogram fastball traveling at 36 meters per second, the impact caused the ball to leave his bat with a velocity of 45 meters per second in the opposite direction. If the impact lasted 0.002 seconds, what force did Reggie exert on the baseball? Okay, so you're going to have a change in velocity, and don't forget it's going to be a bouncing problem, quote unquote bouncing problem. So if 36 is the positive direction, it'll be a negative 45, the opposite direction, minus a positive, which will be quite large. Again, it's bouncing, so it's going to be negative 6,800, negative 6,080 newtons. The U.S. Army's parachuting team, the Golden Knights, are on a routine jumping mission over a deserted beach. On a jump, 65-kilogram Knight lands on the beach with the speed of 4 meters per second, making a 0.2 meter deep indentation in the sand. With what average force did the parachuter hit the sand? Very interesting. I'd like to go parachuting. That would be a pretty cool thing to know. So you're going to use the average velocity calculation, and you're going to understand that the average velocity is 2 meters per second, even though the velocity is going to be, that's the final velocity. The instantaneous velocity is 4 meters per second. So it'll be 0.2 divided by 2, so it'll be 0.1 seconds. That'll be the duration of the impact. So it'll be 65 times 40 times 4, 65 times 4 divided by 0.1. Let's see what that happens. Let's see if you can calculate that before I do. (2,600 newtons). So me, who's 1,000 newtons, would be hitting the beach at 2G, which is significant. So, number 5. The late news reports the story of a shooting in the city. Investigators think that they have recovered the weapon, and they run ballistics tests on the pistol at the firing range. If a .05 kilogram bullet were fired from the handgun with a speed of 400 meters per second and it traveled .08 meters into the target before coming to a rest, with what force did the bullet exert on the target? So again, we need to find the impact, the duration of impact, which is going to be 0.08 divided by 200, not 400. Remember, that's the average velocity that we need, so it'd be half of that. So it'll be 0.08 divided by 200 will be the duration of the impact, which is 0.0004 seconds. 4 times 10 to the negative fourth seconds. So now we're going to take the momentum, which is 0.5 kilograms, times 400, divided by 0.0004 seconds, and that will be the answer. Okay? So it's going to be the momentum divided by the time is going to equal the force. Remember, the impulse equals the force. The impulse equals the change in momentum. So I can divide the change in momentum by the time, and that's going to equal the force, which is 50,000 newtons. Very significant. About 5,000 years ago, in an area located outside Flagstaff, Arizona, a giant 4.5 times 10 to the negative 7 kilogram meteor fell and struck Earth, leaving a 180 meter deep hole now known as Barringer Crater. If the meteor was traveling at 20,000 meters per second upon impact, with what average force did the meteor hit the Earth? Again, we need to know the duration of the impact, and that's what we'll calculate first, given the average velocity, which would be 10,000 meters per second. Don't forget, the 20,000 meters per second is the final velocity, and to get that, it's going to be half of that, and then we'll continue. And also, I'll show you a picture of the Barringer Crater. This is the Barringer Crater. It's absolutely enormous. It's difficult to get a true understanding of the size of it, but you see down in the center, there's a lightness. That's actually a house that the scientific survey teams have used in the past. Here's a little bit better of a shot of the crater, and you can see the ridge around the crater that was formed by the ejecta cloud that came out upon impact, and the forces that must have been involved. Here is a view from one ridge to the next. Some bushes are in the foreground to give you a little bit of an understanding, but it's very deep and extremely wide. The next shot is going to give you a little bit better understanding of some scale involved. Here in the upper right part of the crater, of the ridge, are people walking. And you can see how absolutely enormous it is. So let's do the problem and look at the forces involved in this. So you had this enormous meteor that fell, 4.5 times 10 to the 7th kilograms. Here's the equation to get the amount of time or the duration of the impact given the information here. And it's 180 meters, and it went that velocity, 20,000 meters per second. So you're using 10,000 meters per second because it's average velocity, and 20,000 meters per second was the final velocity. And you can see that the duration of the impact is 18 thousandths of a second. So that's pretty quick, 0.018 seconds. Now we're going to use that value and look at impulse equals change in momentum. We know the mass change in velocity, which is 20,000 meters per second, and then we know the time. And we're going to plug in the mass, the velocity, and the time. And that's going to be equal to 5 times 10 to the 13th newtons. That's 5 with 13 zeros. Trillion has 12 zeros. Okay, in November 2007, astronaut Pam Melroy's history's second woman space shuttle commander flew the space shuttle Discovery to the International Space Station to continue construction. To undock from the space station, Commander Melroy released hooks holding the two spacecraft together, and the 76,700 kilogram shuttle pushed away from the space station with the aid of 4 large springs. If the 232,700 kilogram space station moved back with a speed of 0.5 meters per second, how fast and in what direction did the space shuttle move? So the space station moved back 0.5 meters per second, and so, which is very heavy, it's enormous, and the space shuttle moved the other way. So this is going to be conservation of momentum, and the initial momenta, the sum of the initial momenta is going to equal the sum of the final momenta. So on the left is the shuttle, and on the right is the space station. F for final, I for initial. So we want to solve for the speed of the space shuttle. So we're going to solve for velocity final space shuttle. So now the space shuttle is together initially, and so the left side of the equation, I factor out the velocity of the station and space shuttle together, and then we have the values alone. Now I'm going to flip the equation using the property of symmetry, and then I'm going to subtract the final velocity of the space station from the value, and then solve for the final velocity of the shuttle. So now the next one is I'm going to subtract the first term on the left from the right, and then divide through by the mass of the station. Okay? The mass of the shuttle, sorry, I'm going to divide through the mass of the shuttle. So the next slide, let's wait for it, The next slide has the mass of the shuttle times the final velocity of the shuttle. Now I'm going to divide through by the mass of the shuttle. Okay, so wait for it, and why don't you try to do it right now and try to plug in and see if you can get the correct answer. Okay, see what happens. So that's going to be the final velocity of the shuttle is going to be the velocity of the station and shuttle initial times the quantity of the sum of the masses minus the mass and velocity of the station. And so everything is plugged in. The left term will cancel. You can see the middle term is actually quite large. So the initial motion is going to be 0.5 meters per second. So that will be the positive direction, and the shuttle will be going in the negative direction. And the answer is, you have plenty of time to calculate as we speak. And so you can see that the velocity of the shuttle, the final velocity of the shuttle, is going to be negative. And that makes sense, again, because the initial speed of the final speed of the station is going to be considered positive, and the opposite has to be negative. So the mathematics is consistent with the physics. So it's 116,350 divided by 76,700 is negative 1.52 meters per second. 1.52 meters per second. B says, what is the relative speed of the two spacecraft as they separate? Well, the space station is going 0.5 meters per second in one direction, and the space shuttle is going 1.52 meters per second in the opposite direction. What is the relative velocity? Well, you're not going to say, well, one's negative, one's positive, so you're going to join the two, and it'll be a little over 1. Now, let's say you're on a big highway, and you're going 120 kilometers per hour, and there's a car coming at you going 120 kilometers per hour, going in the opposite direction. If you look in the rearview mirror after it passes you, it's going very fast indeed. And it's coming at you very fast because the relative speed, if you're going 120 one way, 120 the other way, it's going to be 240 is going to be the answer to that. So this will be 0.5 one way, 1.52 the other way. Relatively speaking, it'll be 2.02 meters per second. 8. Tyrell throws his .2 kilogram football in the living room and knocks over his mother's .8 kilogram antique vase. After the collision, the football bounces straight back with a speed of 3.9 meters per second. It's going to be in the other direction, while the vase is moving at 2.6 meters per second in the opposite direction. How fast did Tyrell throw the football? Well, it says opposite direction. Well, there's not two opposites. The football is going forward, so the vase will be a positive 2.6 and the football will be a negative 3.9. So it's going to be conservation of momentum. Initial momenta equals the sum of the initial momenta equals the sum of the final momenta. And we're looking for how fast is the football thrown. So you want to solve for the ball, the velocity of the ball, the initial velocity of the ball. So you're going to want to subtract the momentum of the vase from both sides. So you'll get the right side the way it is minus the momentum of the vase, and then divide through by the mass of the ball. Very simple. Why don't you work on that? There's nothing wrong with your sound, and there won't be any noise, and you try to work with that, okay, and see what happens. You can see already that what I predicted is actually the case. So here you are dividing by the mass of the ball, and that's going to be equal to the initial velocity of the ball. Now we're simply going to plug in our values and crank it out on the calculator. See how the final velocity of the ball is negative 3.9, and the velocity of the vase is positive 2.6, where positive is understood to be true. So the answer to A is going to be positive 6.5 meters per second. So it's going to be going in the same direction, obviously, that the vase is going, so it's going to be going forward. So B says, for the same problem, if the football continued to travel at 3.9 meters per second in the same direction it was thrown, would the vase have to be more or less massive than 0.8 kilograms? Well, let's say it was a wall that's not moving instead of a vase. The football would bounce back approximately or close to 3.9 meters per second. So the lighter the vase, the more chance of it continuing and not bouncing back. So it would be less because the football would not have had as much change in momentum. So the change in momentum has to be such that it's not bouncing at all, that it's continuing to go. If it were a feather, there wouldn't be a question. So intuitively, I think you can see that it would have to be, the vase would have to be lighter. A 300 kilogram motorboat is turned off as it approaches a dock, and it coasts in towards the dock at 0.5 meters per second. Isaac, whose mass is 62 kilograms, jumps off the front of the boat with a speed of 3 meters per second relative to the boat. What is the velocity of the boat after Isaac jumps? Well, the sum of the initial momenta has to equal the sum of the final momenta. And we want to know the final velocity of the boat. It says, what is the velocity of the boat after Isaac jumps? Now, the boat and Isaac, in terms of the initial momenta, are the same. So you can factor that out on the left. And then subtract from it the momentum of Isaac, and then divide by the mass of the boat. Do you see that? Do you see that? So we're going to subtract after the first term after the equal sign. Now we want to subtract that from the left. We're probably going to flip it using the property of symmetry. So I'll let this run and see what you can do with it. Nothing is wrong with your computer. See if you can do this. There, I flipped it. Now what? There you see that term subtracted from the initial momenta expression. And then we're going to divide through by the mass of the boat. We're going to plug in, and then we're going to calculate. See if you can do it before it shows up on the answer shows up on the screen. So we have 0.5 times the sum of the masses minus 62 times 3.5, all divided by 300 kilograms. See what you get. And you see that it's negative 0.22 meters per second. Does the negative make sense? Does the negative make sense? Well, the boat is going towards the docks, that's the positive direction. But when he steps from the boat, he's pushing back on the boat. So Miguel, the 72-kilogram bullfighter, runs towards an angry bull at a speed of 4 meters per second. The 550-kilogram bull charges towards Miguel at 12.0 meters per second, and Miguel must jump on the bull's back at the last minute to avoid being run over. What is the new velocity of Miguel and the bull as they move across the arena? The sum of the initial momenta and then equals the sum of the final momenta. I am factoring out the, I'm not factoring anything, it just looks like I'm factoring out. I just put parentheses around the velocities. And we want to know what the velocity of the bull and Miguel, the bullfighter, is the final velocity. So what we're doing is we flipped using the property of symmetry. Now we're going to determine, now we're going to factor out the velocity of the bullfighter and the bull. We'll factor that out and divide through by the sum of the masses, and then we'll put in and calculate. Let's change the time frame on this. It's getting, you should be able to do this with a sixth sense. Now, as promised, we're going to divide through by the sum of the masses of the bullfighter and bull, and we're going to plug in all the values that are in red in the equation. Now we're going to solve, and we have negative 10 meters per second. Make sure you understand where you get the negative. Where you get the negative. The USS Constitution, the oldest fully commissioned warship in the world, is docked in Boston, Massachusetts. Also known as Old Ironsides for her seemingly impenetrable hull, the frigate houses 56 pieces of heavy artillery, mounted on bearings that allow them to recoil at a speed of 1.3 meters per second. There are 20 cannons, each with a mass of 1,000 kilograms. If a cannon fires a 14.5 kilogram cannonball straight ahead, with what muzzle velocity does the cannonball leave the cannon? So you know, like before, it is the sum of the initial and final momenta. And all I'm doing here is going a little bit more quickly and solving for the final velocity of the cannonball. And you see that it's going to be negative because the recoil was said to be positive. So it's simply the opposite way around. Okay? So the next problem is going to be a little bit more confusing, so we'll slow things down again for the next problem. So you can see that it is negative 89.7 because the recoil was given as positive 1.3, so it's the opposite. Next, on a hot summer afternoon, Keith and Nate are out fishing in their rowboat when they decide to jump into the water and go for a swim. Keith, whose mass is 65 kilograms, jumps straight off the front of the boat with a speed of plus 2 meters per second relative to the boat, while Nate propels his 68 kilogram body simultaneously off the back of the boat at negative 4 meters per second relative to the boat. If the 100 kilogram boat is initially traveling forward at plus 3 meters per second, what is its velocity after both boys jump? Now, there's a problem with this, and that is the water is considered at zero velocity. The speed of the boat is given relative to the water, so that's a conflict. The velocities given for Keith and Nate are relative to the boat. Therefore, the velocities of Keith and Nate have to be corrected for relative to the water. Nate is minus 4, well, with the plus 3 is negative 1, and Keith is going to be plus 2, but the boat is going plus 3, so he's going to be going off plus 5. So it's very important that Nate, Keith, and the boat are all relative to the water. Okay. Our designation subscripts for the problem, to make it easy to understand, will be K for Keith, N for Nate, and B for boat, which should be consistent with the problem. Now, I just want to reaffirm that the new corrected value for Keith's velocity is plus 5, and for Nate, it's minus 1. Very important. Okay, here's the equation. The initial velocity, I simply factored that out from each of the masses because it would just be too long of a problem. So remember that the boys and the boat are all together initially, and that value on the left will equal the total sum of all the momenta final. So the final momenta will be the sum of all the final momenta, and then the initial momenta will be the sum of all the initial momenta. So, and what we're ultimately finding is what is the velocity of the boat after everyone jumps in. So the initial momentum is going to be the plus 3 plus the sum of the masses of the boys and the boat, and the final momentum is going to be the individual momenta. Now notice that Keith is plus 5 and Nate is negative 1, and then the boat has an unknown velocity. That's what we're solving for. Now what we'll do is we will simplify each of those. The initial momentum is simplified to 699 kilogram meters per second. That's an actual momentum, right? And the final momentum is, so far, simplified to that expression. We can add 325 plus a negative 68. That will further simplify that. And then ultimately what we're going to do is we're going to equate the initial and the final sums. So now we have 257 plus 100 times V, and that's going to equal 699. And then we're going to subtract 257 from each side and divide through by 100. So see if that makes sense to you. Take that slide, put it on pause, and study that. And then let's go to the next slide. Okay, so there's the equation. 699 equals 257 plus 100V. And I'm going to subtract 257 from both sides. So 699 minus 257 is going to be 442, and then divide both sides by 100, and you get 4.42 is, and it's positive, and that's going to equal the final velocity of the boat. That will equal the final velocity of the boat. And there it is. It'll be positive 4.42 kilogram meters per second. Lily, whose mass is 45 kilograms, is ice skating with a constant speed of 7 meters per second when she hits a rough patch of ice with a coefficient of friction of 0.08. How long will it take before Lily coasts to a stop? Now, she's going 7 meters per second, and she wants to stop. So what's the change in velocity going to be? It's going to be final 0 minus initial. So it'll be negative 7 meters per second. So the force of friction is also negative. So we want a time. What I'm going to do is I want to know what her weight is, and that's mg, that's 450. It's horizontal. She's not skating up or downhill. So Fw is going to equal Fn. Now with Fn, I can find the friction. Now, think about this. She's going 7 meters per second. That's her initial velocity, and she's going to come to a stop. So what force is acting upon her to stop? Well, the friction. And how do you get the friction? Well, the friction is the coefficient of friction times Fn, and that will equal 36 newtons. Now, I didn't put in the negative signs, and it should be, but there's a reason for that, because I know that the negatives are going to cancel, and I'm going to show you how they're going to cancel. Now, what is the equation for the application of force to bring a body in motion to a stop over a period of time? That's going to be the impulse. The force of friction times delta t equals m delta v. Now, you can see that we want to solve for delta t. So if the velocity is negative, the change of velocity, and the friction is negative, that's going to cancel out, and it's going to be positive. So you'll have a positive t, which you should have. T is not going to be negative. So I left out the negative signs, but they will cancel. The negative signs will cancel, so you're left with a positive delta t. So now all we have to do is plug in 45 kilograms for the mass, negative 7 meters per second for the change in velocity, and negative 36 newtons for the friction. But the negatives cancel, and you're left with a time. So before we do this, it's going to be 45 times 7 divided by 36, and what is going to be the answer here? Can you estimate it? Well, the 45 and 36 is going to kind of cancel to 1. So it'll be a little over 8, 9, 10 seconds, because that'll be like 1.3 times 7. So it'll be about, I'm guessing, about 10 seconds. And 8.75, yeah, between 7 and 10 seconds. That's about right. Because 45 over 36 is, I don't know, 1 point something, 1.4, 1.3. Okay, so the next problem is going to be kind of difficult. So make sure that you have enough time to go through each slide in problem B3. Okay, in a train yard, train cars are rolled down a long hill in order to link them up with other cars as shown. A car of mass 4,000 kilograms starts to roll from rest at the top of the hill 5 meters high and inclined at an angle of 5 degrees to the horizontal. The coefficient of rolling friction between the train and the track is 0.05. What velocity would the car have if it linked up with 3 identical cars sitting on flat ground at the bottom of the track? So V1 is going to be the single car, and V2 is going to be all 4 cars put together, because V1 car is going to hook up. So it's going to be the total momenta of the 3 cars that are 0 and the 1 car that's rolling. You get it? And then the final momenta will be simply the 4 cars put together. Now, we have to find the net force of the ramp car. This first part of the problem has to do with the ramp car. It's going to equal FP minus FF. That's going to be the net, because we got to get the acceleration. And F force is going to be 0.05 times Fn. So we have to apply a little trigonometry. It should be second nature to you. Right now, find Fp and Fn. Okay, very good. Fp is Fw sine theta, and Ff is going to be mu times Fn, which is Fw cosine theta. I'm saying negative because plus a negative is just a negative. So that will give you the net force, that expression. And that's how you should really do physics. You should do it in terms of equations first and foremost. Now they're just converting it to mg because we're given m, and g should be second nature to you. So we're talking about 4,000 kilograms. That's the single car. Remember, we're trying to find the net force of the individual car, which is 4,000 kilograms. So it's going to be 4,000 times 10 times the sine of 5 minus the quantity mu mg cosine theta. And there it is. So plug that into your calculator. 4,000 times 10 times sine 5 degrees minus 0.05, 4,000 times 10 times cosine 5 degrees. And that's going to give you the F net. So do that in your calculator. Try to do that before the next slide comes up. Change of timings. Hope you got it. 1496. I'm sure it's a good year. Columbus was sailing towards South America, causing all kinds of problems. So the net force is going to be 1,496 newtons. Now, I ask you, what does that do for us? What does that do for us? Well, I don't know what it does for us. I'm going to let you. Well, you can can't you get the acceleration using that? So F net over the mass is going to equal the acceleration. Now, what's the acceleration going to do for this? Who cares? What's the acceleration going to do? So, but let's find the acceleration, because when you see F net, you always think acceleration, then maybe something will come to you. We're 5 meters high at the top of the hill. So there's the acceleration. Okay, 1496 divided by 4,000. So it's going to be a very, very slow acceleration. Now, is there any way to calculate anything else? We have acceleration. What are you going to do? Think. We're talking about the ramp car. So the acceleration is 0.37. Okay. I have the F net, the acceleration 0.37 meters per second squared. So now what? What can I do? Remember, I want to find the velocity. What velocity would the car have if it linked up with 3 identical cars sitting on flat ground at the bottom of the track? So I know that sine theta equals dy over d. So what is d? What is just d? Isn't that going to be the ramp? Oh, I see. So there's a distance I can calculate that it's going to be going. So there's going to be one of the motion equations. I'm going to guess that it's going to be something to do with finding maybe final velocity and using A and D. What equation would relate final velocity A and D? D is going to be the distance down the ramp. In other words, I didn't say D hypotenuse. I wanted you to understand that the distance the train is actually, the single train is actually going to be moving. What distance is the actual train going to move? So now I have a distance, I have an acceleration. Those 3 equations, you always want to keep those in mind. Now what? What equation can I now apply? I have D equals 57.4. I have A, which is something 0.3, something or other. So now what? Think. I have to find the final velocity, because that is going to be the velocity for the single train. That velocity. I have the mass and that velocity. That's going to be the initial velocity of the momentum that contributes. And then I have the 3 cars not moving, so that's going to be 0 momentum. And that'll be the sum of the initial momenta. So you can see here that it's going to be V naught is 0. So Vf squared is going to be converted to Vf equals root 2AD. So let's wait for that and just talk about the momentum. Now, I have the final velocity. So the sum of the initial momenta will be the mass of the single car times whatever velocity we come up with, plus the mass of the 3 cars times the velocity, which is 0, so that cancels out, equals the total momenta final will be the mass of the 4 cars times the velocity of the 3 cars, which we're going to calculate. So that's the equation. Can you write that down somewhere? Calculate this equation first. We know that V naught is 0. We said that. So it's going to be root 2 times 0.37 times 57.4. Now, what? We have to actually calculate that value. We have DNA already, and there it is in there. That's all plugged in. And we know that the final velocity of the single train coming down the ramp is going to be 6.5. So this now is the equation. The single car is on the left, that's the ramp car, and then the all cars, and you just plug in. 6.5 is going to be V1F. Okay, now that V1F is going to be initial velocity. So there's the equation, and I just simply use the law of symmetry to switch the sides because I'm calculating actually V2. So now what I'm going to do is I'm going to plug in the values and divide. So it'll be the right divided by the mass of all the cars. Now notice that the single car is the only thing in the numerator, and that's because the 3 cars are not moving, so that cancels out, that's 0. The only thing contributing to the momentum in the initial is the car on the ramp. Does it make sense that the car with the total momentum in the beginning will gain mass and lose velocity? In other words, it's going to hook up with the cars and gain mass. So it's going to go from 4,000 to 16,000. And then the answer is 1.6 meters per second. All right, on a hot summer afternoon, Keith and Nate are out fishing in their rowboat when they decide to jump into the water and go for a swim. Keith, whose mass is 75 kilograms, jumps straight off the front of the boat with a speed of 4 meters per second relative to the boat. That's important. While Nate propels his body simultaneously off the back of the boat at 7 meters per second relative to the boat. If the 120 kilogram boat is initially traveling forward at 6 meters per second, and the final velocity is 8 meters per second, what is the mass of Nate? Now, it says that Keith jumps off 4 meters per second relative to the boat, Nate jumps off 7 meters per second relative to the boat, but the boat is moving 6 meters per second. The boat, 6 meters per second, is relative to the water. So Nate and Keith's velocity has to be corrected for the water, because this problem has to be done either all by the boat or by the water. Clear? Now, the water is stagnant, correct? We have to say that, because they say nothing about the water. So there's something pushing the boat to the right, according to the diagram, correct? And we know that the initial velocity is 6 meters per second. The final velocity is 8 meters per second. Keith has a certain velocity, 4 meters per second off the front of the boat. Nate is going to be, what was it? Negative 7 meters off the back of the boat. You want to vector correction, mechanical equilibrium. So Keith, the correction is going to be what? Plus 10 meters per second. And Nate, the correction is going to be what? What? Negative 1 meters per second. Let's try to participate in this. We know that the initial momenta has to equal the final momenta, correct? Notice I say plural, momenta. All momenta on the initial has to equal all momentum on it. Now this is the problem. K and B, they're all in the boat going at the same speed. It's 6 meters per second, correct? So the initial velocity is going to be their sum of the masses times the initial velocity of the boat, correct? So I'm breaking this down into parts because it just won't fit on the same page. It will be a very, very long equation. So PI is going to equal that expression. Now, we're looking for the mass of Nate, so that's the variable, Mn. Clear? And there's the corrected velocities. So that equation reduces to 1,170 plus 6 Mn. That's the initial momentum, right? 1170 plus 6 mn. Now, the final momentum is going to be 75 times 10 plus negative 1 times mn plus the boat. So that's going to be the final momentum, correct? Remember, we're looking for mn. It's going to be on both sides of the equation. So now I'm going to set I'm going to set the final momentum equal to the initial momentum, correct? Now it's a single variable equation. The left is equal to the right, and I'm simply going to gather my terms. Correct? So there it is. 1170 plus 6mn equals 1710 minus mn. I will reduce that to 7mn equals 540, and 540 divided by 7 equals 77 kilograms. So it is a little larger, but look at the velocity is 7. So what we discussed before, I will discuss in a moment now. And then we're going to do a problem which is very similar to the problem that we just did, but different numbers, and we're going to look for different things, and you're going to do that together in groups. Clear? So that's the end of that problem. Okay? I'll come back and talk a little bit about the size of the momentum contributed by Nate versus Keith. Now, before the problem began, we saw that the final velocity of the boat was going to be 2 meters per second faster than its initial velocity. It was going to go from plus 6 to plus 8. Now, according to Newton's third law, action-reaction, Nate is pushing against the boat. He's jumping off the back of the boat, and the boat pushes on Nate, Nate pushes on the boat. Keith is jumping off the front of the boat. He's pushing against the boat, the boat is pushing against him. If the boat is going to gain velocity, how is he going to gain it? Well, he's going to gain it from Nate. So Nate went off at 7 meters per second. Keith went off at 4. So Nate's momentum must have contributed a greater amount to the forward motion of the boat relative to Newton's third law, action-reaction, than Keith's did. You get that? That's the physics involved here. That's very, 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 very important. So Nate's combined momentum must have contributed more to the increased velocity of the boat. All right, on a hot summer afternoon, Keith and Nate are out fishing in their rowboat when they decide to jump into the water and go for a swim. Keith, whose mass is 55 kilograms this time, jumps straight off the front of the boat with a speed of 4 meters per second relative to the boat, while Nate, 80 kilograms, propels his body simultaneously off the back of the boat at 8 meters per second relative to the boat. If the boat is initially traveling 6 meters per second, and the final velocity is 9 meters per second, what is the mass of the boat? Now notice that Nate contributes an incredible amount of momentum to the boat. 8 times 80, is that correct? 8 times 80? Where that's like 640, whereas Keith, it's a little over 200. So it's almost 4 times, isn't it? So the boat's is only going to speed up 3 meters per second. So the boat's going to be pretty heavy, don't you think? It's going to be a lot heavier than 100 kilograms. What do you say? What do you think? What's your thought on that? Anybody? All right, so what we'll do is we'll go through the same thing, but more quickly. Stagnant water, there's the boat going to the right, plus 6 meters per second, and then the final velocity is plus 9. So Keith is going forward, plus 4 meters per second. Nate is going backwards, and he's going at 8 meters per second. Vector correction is going to be Keith is going to be 10 plus 10, is that what that says? And Nate is going to be minus 2 this time. Okay. The initial and final momentum are equal. So what are we looking for? We're looking for the mass of the boat, correct? So that's the equation. Very similar to last time. They're all on the boat. So it's the sum of their masses times the velocity equals the individual momenta. There's the initial momentum, correct? And we're looking for the mass of the boat, so that'll be a variable. So simplify and then distribute the 6, and you get that expression. And then the final velocity is going to be what we just saw. I'm a little bit behind, but I'm going to simplify the initial momentum, 810 plus 6 mb. So that's 810 plus 6 mb. Is that what I just said? Or no, did I say something different? Anyway, so now I'm going to take that, and now I'm going to simplify the final momentum, which is 390 plus 9 mb. I'll set the initial equal to the final, and I have that expression coming up. There's again the simplified final momentum, 390 plus 9 mb. Now I'm going to set them equal to each other, and it will be, the initial is 810 plus 6 mb, and then 390 plus 9 mb. Kind of being a little bit exact, aren't I? But it gives you a chance to see it. So there's the equation, and then 3 mb equals 420, and 420 divided by 3 is going to be in excess of 100, certainly, be 140 kilograms. Right? Any questions? I'm in class talking to my wonderful, wonderful students. Any questions? Pretty good? Yes? No? All right. That finishes the video, and I'll post that online, and good luck.